Okay. Yeah, it's going. Okay, polar and nonpolar bonds. All right, very simple. If you have a bond on a covalent compound, it's either going to be polar or nonpolar. And it's very easy to tell the difference. If they're nonpolar, they have no partial separation of charge because they typically involve two atoms of the same element bonded together, like a hydrogen molecule, where you have two hydrogen atoms bonded together, or even two fluorine molecules bonded together, because both atoms have the same electronegativity. Now, what did we say electronegativity meant? Attraction for valence electrons, right, or attraction for electrons out in the valence shell. Now, if they have the same electronegativity, it really doesn't matter how high it is. They're going to be basically equally sharing out the bonding pairs of electrons. So those electrons are going to spend essentially as much time with one atom as they do with the other. And that's going to give us then what we call a nonpolar bond. All right, now, what if we have a polar bond? Well, here there is going to be a partial separation of charge, and that's largely going to be brought about by the fact that the two bonded atoms have different electronegativities. All right? And if they have different electronegativities, then you're going to find that the shared electrons spend more time, if you will, with one atom than they do with the other. And a partial charge develops. A partial separation of charge develops. So, look at the electronegativities. If they're the same atom, two atoms of the same element, we should say, they're going to have the same electronegativity. They're going to have the same affinity for the shared electron pairs, and you're going to have a nonpolar bond. But if they're different atoms, two atoms of different elements, they have different electronegativities, they're not necessarily going to share things out evenly, and you're going to get a slight imbalance, and thus a partial separation of charge. Now let's just put some drawings up here on the board and demonstrate what we mean by nonpolar, and then we'll look at polar. Okay? Alright, so let's see what we can do now to get the screen up. Alright, let's see. How on earth is that? There we go. Now, there we go. That'll work. Now, let's take a nonpolar case first. Let's suppose we have a hydrogen molecule. They're the two hydrogen atoms bonded together by a shared pair of valence electrons. What did I do with my markers? There they are. All right. They both have the same electronegativity, so they both have the same affinity or attraction for those. And if we were then to draw the electron cloud about the molecule, well, it's going to turn out to have a nice, even, symmetrical shape, and there really isn't any partial separation of charge. But what if we kick it up a notch and form a molecule that has a hydrogen atom bonded to a chlorine atom? Which atom is going to have the higher electronegativity? Well, now remember the trend. Where are they the highest? All right, chlorine is going to be higher because remember, fluorine is the highest, and as you move to the right, or excuse me, to the left, I'm thinking backwards again, or down, they decrease. I think we talked about that last time, didn't we? All right, fluorine's the highest. As you go down the group, it gets lower. As you move off to the left, it gets lower. All right? Hydrogen's very far to the left, so it's low. All right, chlorine's higher, and so it's going to tend to want to draw those shared electrons closer to the chlorine and away from the hydrogen. So if we kind of shade in here a electron cloud about this thing, it gets to be a little thicker on the chlorine end than it does on the hydrogen end. Now, what is the charge on a chlorine, or excuse me, on an electron? Negative. All right. So if you've got a concentration of electrons on this chlorine end, then you're going to find that that end of the molecule tends to become slightly negative. All right? And we can show that partial negative charge this way. In fact, what we have there is a lowercase delta. It's a Greek letter. And it's just like taking an S and closing up the loop is good enough. All right? Now, if that end of the molecule is becoming partially negative, what's going to happen to the other end? Huh? Positive, yes. Slightly positive. Now, it's not like +1, -1. It's not that big of a difference. But the chlorine end is going to become partially negative. The hydrogen end, by extension, is going to have to be partially positive. We have to have balance. Why? What's the charge on any molecule? Neutral. 0. And the molecule is neutral as far as the overall molecule charge is concerned. It's 0. That hasn't changed. But because the chlorine has the higher electronegativity and is drawing the electrons more to that side, we're getting a little more electron dense, a little thicker with electrons over here. That end is going to become slightly negative. The hydrogen end, by extension, is going to have to become slightly positive. All right? So we have a polar bond, and we even have a polar molecule here. Now, there's another way to show that, and this is what's called a dipole notation. All right, and how is it set up there? And we use these for the bonds. We use these dipole notations for polar bonds. Where does the arrow point? Who's it pointing toward? Well, and what about the chlorine and its electronegativity? It's higher, right? The one with the higher electronegativity is the one the arrowhead points toward. Now, what about the one with the plus over it? That's the one with the lower electronegativity. All right? So, with the dipole notation, the arrow points toward the element with the higher electronegativity, and the plus goes over the one that has the higher electronegativity. All right? And remember the trend on electronegativity. The highest element to have the highest electronegativity is fluorine. And you know where it is on the, have you got your periodic tables handy to look at? You see where fluorine is, all right? Now, as we said, as you go down that group, down from fluorine, electronegativities tend to decrease. As you move to the left, away from fluorine, they tend to decrease. What about the noble gases and electronegativity? What do you say about them? They don't have one, because they have a filled valence shell. There's no affinity to attract any extra electrons into it. All right? And another thing that you probably notice with that, non-metals tend to have higher electronegativities than metals. Metals tend to be very low. All right? All right. Now, simple enough, isn't it? All right, so there we have a non-polar bond, two atoms of the same element. They both have the same electronegativity. Equal affinities for the shared pair of electrons. They spend really as much time with the one atom as they do with the other. But here we have two different elements, atoms of two different elements. One, the chlorine in this case, has the higher electronegativity. It tends to pull the electrons toward it, away from the hydrogen. So the chlorine end of this molecule takes on a partial negative charge, and the hydrogen end, by extension, will have a partial positive charge. And remember now, the molecule, both molecules, have a neutral or zero charge on them, because molecules are neutrally charged. All right? But here we have a partial separation of charge, making this a polar bond and a polar molecule. So now, if we have a two-atom molecule, like we have up here on the board, what is their shape? What's their shape? What is the shape of a two-atom molecule?
Linear.
Linear. All right, so if it's made up of two atoms of the same element, is it polar or nonpolar? Two atoms of the same element? Nonpolar. And if it's made up of two atoms of two different elements, it is likely to be polar because of the difference in electronegativities of the two elements. All right, the two atoms. Now, it's pretty simple, isn't it? Yes. All right. So now, let's see if we can get this to stay down without going full tying and binding. And, oh, there we go. And let's move on now to, and we talked about that, all right, to the shapes of molecules. And as we already know, the two atom ones are linear, and I got to move this along because I've got to resort these things. And unfortunately, that isn't always easily done. All right, now, polar, nonpolar molecules, just as we can have polar, nonpolar bonds, we can have polar, nonpolar molecules. We've already seen that for the two atom ones. Polarity depends really on what the atoms are and the shape of the molecule. All right. So, if we continue on from there, we already know with two atom molecules, if they're two atoms of the same element, it's nonpolar. If they're two atoms, two different elements, it's likely to be polar because of that difference in electronegativity. Okay. So, if we continue on then, for two atom molecules, we've already said that. All right, so let's kick it up a notch and let's get to three atom molecules. And here we have a couple of differences. All right, we're looking at a nonpolar sort of molecule if we end up with a linear-shaped molecule. So we're thinking here of three atoms, two different elements, and a linear shape. It's going to work out to be nonpolar. Now, let me just get my little box of models out to refresh our memories again. And so, I'll just lay that aside for now. And let's just take a look at an example of one of these. All right? Now, let's see if we can put this up. Now, all right, here is a good example of something that would give us a linear-shaped molecule. And what is the name of that compound? Carbon dioxide, right. What's going to go in the middle? What's going to be the central atom? Carbon, right. And how many valence electrons does it have? 4. All right, and then we're going to put the oxygens over here on the end. And how many do they have?
6.
Yes. All right, so there's one of them, and here's another one. And now we start pairing up the electrons. And of course, if we pair up the unpaired ones, it works out very nicely. We end up with that kind of a situation there, and that situation there. So we end up with two double bonds, right? All right, a double bond between the carbon, the central carbon, and each oxygen. Now, as we know, on that central carbon atom, as we mentioned last time, there were no unshared pairs of electrons. all that we have on the central carbon are bonded pairs of electrons, right? Well, let's take a look at this little model again. Here in the center is the carbon. There in red on either end are the two oxygens. All right? Now, what is the shape going to be? Well, it's linear, okay? Because we have, in essence, a 180-degree angle between those two sets of double bonds. All right? It's linear. It's all lined up in a row. The nuclei of each atom in a single plane, in the same plane. All right? Now, let's take a look at the bonds. All right, let's just redraw this as a structural formula here. And let's take a look at the electronegativities of our two bonded atoms. All right. Carbon and oxygen. Which one is likely to have the higher electronegativity? Oxygen is, isn't it? Because it's the farthest to the right. Okay? It's getting closer to fluorine, isn't it? All right. Carbon is likely to be somewhat lower. All right? So now, would a carbon-oxygen bond be a polar or non-polar bond? Is it likely to be polar or non-polar? And why? Well, what was the difference? When you had a non-polar bond, what did you have bonded together? Two atoms of the same element, right? What did you have when you had a polar bond? Two atoms of two different elements, right? Well, carbon and oxygen, are they the same or different elements? They're different. So, I would predict, would you not, that there might be a difference in their electronegativities, right? Because I think we just said oxygen's likely to be higher, carbon lower. So, in other words, what we're saying is that a carbon-oxygen bond is a polar bond, right? Yes. All right, and if we put our dipole notation up here, well, for that carbon-oxygen bond, I think it would look like that. The arrowhead points toward the element with the higher electronegativity. That's oxygen in this case. And the plus goes over the element with the lower electronegativity. In this case, that's carbon. All right? But I have two carbon-oxygen bonds, so I need to put up here two of those dipole notations. Okay? Right? Now, what is the angle between these two things? 180 degrees. They're going directly opposite each other, are they not? Okay? That would seem reasonable. Well, now, let's have a little demo. And for that, and I'm not going to hit you or anything, I need two volunteers from the audience. Come on down, any two people. Oh, come on, don't be bashful. Come on. Excellent, all right. Well, now we'll need three later, but two for now. Now, here's what we're going to do. Okay, now let's see. I'll be the carbon, and you're going to be the oxygen. You're going to be the oxygen, and you're going to stand, get over here on the ends. And you're going to have to hold it right on the end because. Now, what's happening here? They're pulling the electrons toward them, right? Away from me, right? They're more electronegative. All right, now I want you both to start pulling on the reader sticks. Am I going anywhere? No. All right, good. That takes care of it. Thank you. Now, what point does that make? Well, it means basically that since these are of equal magnitude, pulling opposite each other, they're going to cancel each other out. And because of that shape, and because they're canceling out, there is no what we would call dipole movement. No dipole movement on this molecule. And if there's no dipole movement, I didn't go anywhere, did I? No. Well then, it's going to turn out to be a, lo and behold, non-polar molecule. All right. Now, even though we have two polar bond sets here, they cancel each other out because of that linear shape. If I take this model and I start pulling out on those oxygens, is the carbon going anywhere? Is the molecule moving anywhere? No. It's canceling out, there's no net movement, and therefore it is a nonpolar molecule. All right? Well, that's simple, isn't it? Well, let's kick it up a notch and look at another example. All right. I probably should have left that one. Now leave this one here. All right. All right. Let's take this one. What's the name of this thing?
Water.
Water. We go with the common name for it. All right. In the center we have our oxygen, right, with its 6 valence electrons. And then we're going to stick a hydrogen here, and we're going to stick a hydrogen here. Now, if we go back and apply our molecular shape rules that we learned the last time, what have we got? We've got a 3-atom molecule with 2 different elements. There are 2 unshared pairs of electrons right on the central atom. So what does that do to the shape of the molecule? It gives us a bent or nonlinear shaped molecule just like this, where the red ball would be the oxygen and the 2 hydrogens here. The unshared electron pairs, well, they're somewhere up here. And remember now, all these electrons on the oxygen are repelling each other, trying to get as far away as they can. The hydrogens have to go along for the ride because they're attached by way of those shared electrons. And you end up with this kind of a situation, and I think you'll end up with something that's about 109.5 degrees between them. I wouldn't worry about that number, all right? But it is bent. It's nonlinear. Now let's go back and take a look at the bonds. We have 2 hydrogen-oxygen bonds. Are hydrogen-oxygen bonds polar or nonpolar? And why? Well, again, let's consider. What do we have bonded together when we have a hydrogen-oxygen bonded? It's polar. Why? 2 different elements with 2 different electronegativities, right? There is a difference in electronegativity. That's going to make a polar bond. All right, now let's put our little dipole notations up there. So when we put the dipole notation in place, which element is the arrowhead going to point at? The oxygen, right. The oxygen would have the higher electronegativity. So the arrowhead points toward the oxygen, the plus sign goes over the hydrogen. Well, what about here? Exactly the same thing. All right? Now, could I have my 2 volunteers back, or 2 others if somebody else wants to jump up and run up here? Everybody must be bashful and shy today. All right, now, I'll be the oxygen, they're going to be the hydrogens. So we need one of them here, and one of them here. All right, so there we go. Let's get a hold of our sticks. Now this time you're going to push, right? Because you're pushing toward the oxygen. So push. What's happening that time? Am I standing still? No, I'm moving. All right, now what have we got? A polar. Yes. we have net dipole movement. I think this blue marker's dying as we go. And therefore, we have a polar molecule. All right? Polar this time. There is net movement. Oh, I forgot to pass the sheet around. All right. So there is this kind of polar molecule. This one was nonpolar. Why? Well, because of the linear shape, the dipoles basically cancel. There's no net movement. It's nonpolar. And this one is polar because of the bent shape where the two dipoles basically reinforce each other. All right, now there's one other little wrinkle to the prune. All right, because this is a polar molecule, we need to use our little notation with the lowercase delta to show the areas of partial positive and partial negative charge. So on this molecule, which end, the hydrogen end or the oxygen end, is likely to be partially negatively charged?
The oxygen?
Yes. So the oxygen end is going to take on a partial negative charge. And what about the hydrogen ends? Well, by extension, they're going to be partially positive charge. All right? They take on a partial positive charge. There you go. Just that simple. So water is a polar, in fact, pretty highly polar molecule. Carbon dioxide, because of the linear shape, is nonpolar. And we don't have any partial separation of charge over it. Yes?
Do you only draw the delta things if it's polar?
Well, if it's polar, you draw the delta things, that's right. And if it's non-polar, just leave them off. Okay? Yes?
So, any molecule that is bent
Yes.
is going to be polar.
Probably will.
Okay.
Yes. Now, if you've got something like ozone, which is O3, it probably isn't. Okay.
Yeah.
But that's an odd one.
Okay.
But generally speaking, yes. If it's a 3-atom molecule with a bent shape, it's going to be polar. Okay? I can't think of any exceptions to that.
Okay.
Unless, you know, it's 3 atoms of the same thing. And that's an odd one. All right? There we go. Now, that's pretty simple, isn't it? All right, so let's see what we can do with the screen. And the next slide is something we really already talked about, or the next line, because if they're bent, it is going to be polar, just like the water was, okay? So, pretty simple. 3-atom molecules, if there are no unshared pairs on the central atom, it's a linear shape. If it's a linear shape, it's nonpolar. All right, if it's a 3-atom molecule with 2 different elements, bent or nonlinear shaped, it's going to be polar. All right, because the dipoles really reinforce each other and get net dipole movement. Okay? Now, let's kick it up a notch to a 4-atom molecule. Oh, now, this isn't hard at all. All right. Now, as a general rule, if it is a trigonal planar shaped molecule, it's typically going to be nonpolar. Now, there is, and I'll show you an exception to that. But for the most part, if it's trigonal planar and it's only 2 different elements, it's nonpolar. All right? Now, if it's 3 different elements, that's a different story. We'll see. All right. If we have something that is trigonal pyramidal, well, they turn out to be polar. I can't think of any exceptions to that. All right? Well, we'll take a look at both of those. All right? So we'll look at the trigonal planar case. And we'll take a look at the trigonal pyramidal case and see what we can shake out when we shake the tree of knowledge. Okay? All right. Well, let's see what we can do here. All right. Good thing I have glasses on. I'm put mine out. All right, now let's see. Okay, boron trichloride. Why am I down there? Let's see. Boron trichloride. There's one that's going to be trigonal planar. All right, we put the boron in the center, and we put the chlorines out here on the ends. And the angle between these is probably about 120 degrees, because they're all evenly spaced out, just like this model, where the boron will be the pink ball in the center, and then the 3 chlorines out there around it, forming this trigonal or triangular shape, and planar because all the atoms' nuclei are lying in the same plane. All right, now, if we consider that shape, that trigonal planar, which element is likely to have the higher electronegativity? The chlorine is, right. Where do you find chlorine on your periodic table?
All the way to the right.
All the way over in group 7, and where's boron? Group 3, isn't it? All right. Now, all right, so chlorine's higher, so I think when we put our little dipoles up here, we're going to get something akin to this. The arrowhead points toward the chlorine and away from the boron. All right, now, I need 3 volunteers this time. Come on, come on. Okay, there's 2. 1 more. Thanks for being a good sport. Now, here, let's see. We got to get 2 in front. I'll have to get the angle set here. Oops, I'm going to pop it. Okay. Okay, something like that. And then 1 behind. All right. Right back here. All right, now what's happening here? You're all going to be pulling, right? Am I going anywhere? No. All right, very good, thank you. All right, there we go. So what's happening here? All right, the nice even angle between all those, they're canceling each other out. So we have no net dipole movement. And how would you classify the molecule? Non-polar. All right. Now, just to cloud the issue a teensy bit, let's try this one on for size. All right. Now, what would be the shape of that molecule? It's a 4-atom molecule. There aren't any unshared pairs on the central atom, right? So it's trigonal planar as well. Yes, trigonal planar. Now, let's put up the dipole notation and let's see what happens with it. All right, we have a carbon-oxygen bond. Is that a polar bond? Well, it was the other time, wasn't it, when we did it in carbon dioxide, right?
Will all of them be going in
Well, which way is it going to point?
to carbon?
No. Oxygen's higher.
Okay.
So it's going to point that way. Now, we also have 2 carbon-hydrogen bonds. Who has the higher electronegativity this time? Carbon does. So, we're going to have one like that, and we're going to have one like that. Now, can you do that in your head, or do you need the sticks?
So it's going to be polar.
Well, let's have the sticks. Let's have the stick people come back. All right, we need 2 people to be hydrogen. I'll be carbon. 2 people to be hydrogen. We need somebody to be oxygen. So there's one. There's the other. And then the one behind. Swing around and you can grab it. All right, now, here's the deal.
I need 2 of these.
You're pulling. No, one's enough. You're pulling and they're pushing. All right? So start moving. Oh, okay. Now, what's happening here?
It's polar.
It is. Well, yeah. They're helping you out, too. So they're not canceling out this time. So this one turns out to have net dipole movement, and therefore it is polar. All right. Now they're both trigonal planar shaped. What's the difference? Why is the boron trichloride nonpolar and the other one polar?
Do they both have no unshared pairs?
No unshared pairs on the central atom, no. Huh? Well, but what? Yeah, we have the dipole movement, but why do we get it? What's the difference? Look at the composition. How many elements are making up boron trichloride? 2 different elements. How many do we have in the other case? 3 different elements. That's what makes the difference. Okay? All right, so there you go. All right, pretty simple. Most of the time, trigonal planar, and especially if it's trigonal planar with just 2 different elements, it's nonpolar. 3 different elements, well, probably going to be polar. There's going to be some difference there. All right, now let's go on to the next one, and that's the trigonal pyramidal, and that one is ammonia. Is a good example for it. And with that one, remember, we have the nitrogen in the center, but what is the big difference here between it and these?
You have an unshared
There's
pair.
an unshared pair of electrons on the central atom. So, to pull that one out, here is the ammonia molecule. The blue ball representing the nitrogen, and it would have these 2 unshared pairs of electrons up here. And then the brownish balls, well, they're each a hydrogen. All right? And because there's an unshared pair here, it's repelling all these bonding pairs and giving us then the case where the nitrogen is in a higher plane than the hydrogens. All right. Now let's go ahead and put up our dipole notation. All right. Who has the higher electronegativity this time? Hydrogen or nitrogen?
Nitrogen.
Nitrogen does. So, I'll have one there, and one there, and one there. Now, this time, I'll just do it this way. Let me just take my sticks, and I'll set them something like, something like this. All right, now what's happening? The movement is coming up toward the nitrogen, which is up here where my thumb is. And so if I'm pushing up on those, I'm getting movement. All right? So they're not canceling out, they're reinforcing each other. And so here we have net dipole movement. And therefore we have a molecule that is polar. A polar molecule. All right? So that's pretty simple, is it not? So if we have a trigonal pyramidal molecule, it's probably going to turn out to be polar. All right? Even if it's just 2 different elements that make it up. Okay? So, pretty simple. Well, let's just kick it up one more notch. And let's go to a 5-atom molecule. All right, and really, what's the shape for a 5-atom molecule? It's tetrahedral. And a tetrahedral molecule is nonpolar if it's only made of 2 different elements. All right? Now, if it's 3 different elements, well, that could be a different story. But we'll look at both cases. Good heavens. Right? Well, let's take a look. Let's just take a look. You seem skeptical. All right. All right. Now let's see. What's this? All right. Now we had methane. And that one is the one that CH4 is the molecular formula. So we have the carbon in the center, and we have the 4 hydrogens out here on the sides. All right, now let's go back and let's put up our dipole notation for each of the carbon-hydrogen bonds. So in a carbon-hydrogen bond, who has the higher electronegativity, carbon or hydrogen? Carbon. All right, so if I draw my dipoles, they're all pointing in towards carbon. And the other trick with this is, of course, that they all cancel each other out. All right, here's a model. Let's do it this way. There's the model. The carbon's here in the center where the black is on this. And each of these aqua balls would be the hydrogen. All right, so if they're all pushing in toward the carbon, is it going anywhere? Nope. They all cancel each other out. So therefore, in this case, there is no net dipole movement. All right, and therefore it is a non-polar molecule. Now, let's kick it up a notch, shall we? Now, what do we have here? We have something that can be called methyl chloride, but we don't need to worry about the name of it. All right, carbon, hydrogen, we've said carbon's higher on the electronegativity scale. So for all of these, we put our little dipoles up, and there they go, pointing in toward the carbon. But now, what about the carbon-chlorine bond? Chlorine has a higher electronegativity this time, right? Are they all canceling out this time? No, they're not. So if we took a look at this one using sticks, models, or whatever, we would find there would be net dipole movement. And as a result, this one is going to turn out to be somewhat polar. A somewhat polar molecule. All right? Now, let's put our little deltas up there to show the areas of partial positive and negative charge. Where's the partial positive charge going to go this time?
By the hydrogen?
Yeah, the hydrogens, right. And since we have 3 hydrogens, we'll have 3 of these pluses. And the chlorine end is the one that's going to be partially negative. Okay? Now see, that isn't hard, is it? Is it? No. Now let's just kind of summarize a bit for our take-home messages. All right, if you're wanting to look at whether a molecule is polar or nonpolar, you first have to look at whether the bonds involved are polar or nonpolar. All right, so if we start with a 2-atom molecule, what shape does it have to be?
Linear.
All right, if it's 2 atoms of the same element bonded together, the bond between the two is nonpolar, and the molecule is nonpolar. All right? If it's two atoms of two different elements, the bond between them is polar, and the molecule is polar as well, has to be. All right, if we kick it up to 3 atom molecules, if we end up with a linear shape made of just 2 different elements, it's going to be nonpolar because the dipoles cancel out because of that shape. All right? They're directly opposite each other. Pulling away or pushing in doesn't matter. There's not going to be any net dipole movement, and it's nonpolar. If it is a bent or nonlinear molecule, it's almost inevitably polar because what do we got here? There are 2 polar bonds. If it's hydrogen, oxygen in the case of water, they're reinforcing each other because of the way they sit on here, the angle between them. They're not canceling out, they're reinforcing. There's net dipole movement, and it is a polar molecule. Now, if we go to a 4-atom molecule and a trigonal planar shape, if it's only 2 different elements, it's nonpolar. Again, because the dipoles cancel each other out, and there's no net dipole moment. If it's 3 different elements, it's probably going to be polar, because there's probably going to be one that's a higher electronegativity than the others, and you're not going to cancel everything out. If you have a trigonal pyramidal shaped molecule, it's almost inevitably polar regardless of how many different elements are there. Okay? Because in this shape, there's at least an unshared pair on the central atom, and that one's probably going to be one with a higher electronegativity than the others, and you've got the dipoles all reinforcing each other, just pointing right up here, basically causing that to move. And then if you have a 5-atom molecule with a tetrahedral shape, if it's only made of 2 different elements, it's nonpolar. If you go with 3 different elements, well, you better take a look at what happens. Because probably if it's 3 different elements, it's probably going to be polar. All right? But if it's only 2, it's nonpolar. They all cancel out. Okay? Now that's not hard, is it? No, you just need to think about it. That's all. All right, so let's see what the next wrinkle on the prune is. All right, now let's see here. I've got my slides in the order I want. If not, I have to skip around. Oh, perfect. Interparticle forces. Now, particles. We're talking about particles here. That could mean atoms, ions, molecules. Okay? Atoms, ions, or molecules. Now, forces of attraction between particles, that's all the term interparticle force means. So we're looking at forces of attraction between atoms, ions, or molecules. All right? Now, the strongest of them, and there are just 4 of these, and we're going to take a look at each. Ionic bonds. Now we know what ionic bonds are. Good heavens. What is an ionic bond? How would you define it? Ionic bond, what is it? Yes, it's a bond between a cation and anion, or another way to say it, force of attraction between cation and anion. Right? Those are very strong bonds. In fact, most ionic compounds are solids at room temperature because the bonds are so strong that the ions are held in essentially fixed positions. They don't move much with respect to one another. All right? hydrogen bonds. Hydrogen bonds are strong, but they're a bit weaker than ionic bonds. All right? We're going to see examples of that. They're very important. Dipole forces are a little weaker yet. They're not as strong as hydrogen bonds. All right? Now, just to give you a little hint, obviously, ionic bonds are only going to apply to ionic compounds, right? Because that's what's made of cations and anions. Hydrogen bonds, dipole forces, well, those are really only going to apply to polar covalent molecules. Okay? So, if we're talking about hydrogen bonds or dipole forces, they only apply to polar covalent molecules. They don't apply at all to ionic compounds. And they don't apply to non-polar covalent molecules because the next one applies to them. That's what are called dispersion forces. And dispersion forces are the weakest of the lot. And dispersion forces, as we shall see, apply only to non-polar covalent molecules. That's it. So you see, if it's an ionic compound, we've got an interparticle force that applies, one that we know and well love, ionic bonds. If they are polar covalent molecules, there's always going to be the dipole forces, but a lot of times, in addition, hydrogen bonds as well. And if they're non-polar covalent molecules, which one's going to apply? Dispersion forces. All right, there we go. Are they alike? No, not really. Although there's going to be a little bit of blending here in a bit. Hydrogen bonds, let's take a look at them first. Well, a lot of polar covalent molecules can do them, of course, and two that are infamous for doing it are water and ammonia, but there's going to be a lot of others that do too. And we're going to see more of this when we get into the organic compounds next week. All right, hydrogen bond. What is it? Here's the definition. An attraction between an unshared pair of electrons on an atom in a molecule and a hydrogen atom on an adjacent, and we probably should also throw in there closely spaced, molecule. Now, what do we mean by something being adjacent? Close. The neighbor, in other words. And I mean close neighbors in this case. All right, so an unshared electron pair on one atom on a molecule, and typically on a different molecule, a hydrogen. All right, the two are going to get together. They attract each other. Now, at the bottom of the screen is just one little tidbit to file away for next week. All right, if a molecule, a large molecule, like protein, can twist and bend on itself as they do, they can form hydrogen bonds within that molecule. So it doesn't have to be between two molecules if it's a big molecule. Small ones, yeah, they do. All right? Now let's take a look at a water molecule model again. And so, as we can see, the red ball would obviously indicate the oxygen. The oxygen, as we've already said, is slightly negative with respect to the hydrogen ends, right? It's a polar molecule. And what do we have up here, like here and behind the screen? What would be up here? It's not showing. Two unshared pairs of electrons, right? That's what gives it that bent or nonlinear shape. Well, let's put a bunch of water molecules together in close proximity. And what do we come up with? Voila! Hydrogen bonds forming between closely spaced adjacent molecules of water. Here's a hydrogen on one molecule. Here's an unshared pair of electrons, even though it isn't shown on another. All right? There's a hydrogen bond between the two molecules. Same deal here, here, and here. Now, those hydrogen bonds account for many of the properties that we associate with water. What is the physical state of water at room temperature? It's a liquid. Now, in a liquid, you have to have strong enough interparticle forces to hold the structural units, the molecules in this case, together. So they can't go flying away from each other. But they're not held so tightly that they can't move with respect to one another. You know, that's the waves in the ocean, right? All right. What happens, however, if you take some water and you stick it in an ice cube tray and you pop it in the freezer and you walk off for a few hours and you come back? What's the physical state now for those water molecules? It's a solid. You've got ice. What's happened? Well, you've taken away heat. The molecules are now slowing down. They're not moving so fast. The hydrogen bonds get stronger because the molecules tend to move a little closer together. And they get held in fixed positions, and now you've got a solid. Remember, now in a solid, the interparticle forces are strong enough to hold the structural units, whatever they are, in essentially fixed positions. Very little motion. Very little motion. Now, take the ice cube, drop it in a saucepan, pop it on a burner, and crank up the heat. What's going to happen? It's going to melt, and then it's going to do what? It's going to boil, and it's going to evaporate. That's right. You're going to be changing that to a gas. Now, what's happening when you're doing that? Those molecules are picking up heat. They're starting to move faster. They're getting further apart. Eventually, they get far enough apart that they break the hydrogen bonds, the shackles that have been holding them together, and where do they go? Off on their own. Because in a gas, you have virtually non-existent or non-existent interparticle forces. It's every molecule for himself. They've got high enough energy they can avoid each other. And they do. All right? Now that's simple, isn't it? So hydrogen bonds really account for that ability of water to be either a solid, liquid, or a gas, depending on the temperature. They're pretty strong. They want to hold the molecules together. But in order to do it, the molecules have got to be pretty close together. If they move apart, what happens to the hydrogen bonds? They break. And then you have a gas or a vapor. All right? What is a hydrogen bond? It is a force of attraction between what two things? Unshared pair of electrons and a hydrogen. Right. So if you don't have an unshared pair of electrons, don't worry, you can't have hydrogen bonds. If you don't have any hydrogens around, you can't have any hydrogen bonds. Now that's simple, isn't it? Isn't it? All right. As we've already said, hydrogen bonds are weaker than ionic bonds. All right. Okay. And we already said that. Oh yes, this was cute, so I put it in. Dr. Cordner, when she was talking about hydrogen bonds in her class, had a sweatshirt made, and here it is. It says the name is Bond, hydrogen bond. And what do we have here? There's an oxygen with an unshared pair of electrons, and what's right there? A hydrogen. All right, so there we go. You're all getting tired, I know. All right, dipole forces. Well, now these are cake. These are even cake here, probably. All right, what are they? Well, they're forces of attraction between the opposite poles of closely spaced adjacent polar covalent molecules. Okay? Forces of attraction between the opposite poles of closely spaced adjacent polar covalent molecules. Well, now you write that down and I'll give you some time to digest it. It's really very simple. Let's take a couple of polar molecules. In fact, we could even use water as the example if we want. Which end of the water molecule had the partial negative charge to it? Oxygen. That's a pole, right? That's the negative pole. All right, which end of the water molecule had the partial positive charge to it? The hydrogen. Well, there's another pole, one with an opposite charge, right? So if you put a bunch of water molecules together, even though the hydrogen bonds tend to take precedence, you're going to get something that would look very much like that. Here is a positive pole of one, there's a negative pole of another. Opposites attract, right? There you go. All right? Well, that's simple, isn't it? Yes, it is. No, you're getting tired, but that's all right. And of course, as we said, these only apply to what kinds of substances? Polar covalent molecules. So, hydrogen bonds and dipole forces typically apply only to what kind of substances? Polar covalent molecules. That's right. Okay? Dispersion forces, the weakest of the lot, much weaker than any of the others, to be honest. What have we got here? Forces of attraction between closely spaced adjacent non-polar covalent molecules. So, to whom do these apply? Non-polar molecules. Non-polar only. All right? If we had a chlorine molecule, could these apply? Perhaps. We'll take some examples here in a bit. All right? Forces of attraction between closely spaced adjacent non-polar molecules. That's all dispersion forces are. All right. Now, we said they only apply to non-polar molecules, and here's another interesting tidbit, which we'll demonstrate here in a bit. All right. Atoms that have more electrons tend to have stronger dispersion forces. All right? Atoms that have more electrons tend to form stronger dispersion forces. Let's take some examples. And we'll go to the periodic table, so have it handy. Chlorine. How many electrons? I'm not talking valence electrons, I'm talking total electrons. How many electrons does a chlorine atom have? 17. All right. What is the physical state of chlorine at room temperature? A gas. All right. It's a non-polar molecule, right? What kind of interparticle forces could exist? Dispersion forces. Are they very strong in the case of chlorine? No, practically non-existent because it's a gas. Let's kick it up a notch. Drop down a line. Next element, bromine. What is the physical state of bromine at room temperature? It's a liquid. Probably has slightly stronger interparticle forces, right? All right. If it is a bromine molecule, is it polar or nonpolar? Nonpolar, right. Same electronegativities between the two, right? But it has stronger dispersion forces. How many electrons does a bromine atom have total? 35, okay. Drop down to iodine. How many electrons does an iodine atom have? 51? 53, okay, that sounds about right. What is the physical state of iodine at room temperature? A solid. What about the strength of the dispersion forces there? Because that's all going to have, right? It's non-polar, right? They have to be pretty strong, wouldn't they, if it's a solid? Because what did we say about solids and the interparticle forces? They have to be strong enough to hold the structural units in fixed positions. Iodine has the strongest of those dispersion forces of those three elements. Bromine would be a little weaker because it's a liquid. Chlorine would have the weakest or virtually non-existent because at room temperature it is a gas, right? Who formed the strongest dispersion forces of those three elements, chlorine, bromine, or iodine? Iodine. Who has the most electrons? Iodine. Well, isn't that interesting? Now, that leads us to another wrinkle called solubility. And we'll just start it today, but we'll finish it off Tuesday. Now, you're lucky. You all get to meet Tuesday. The Monday, Wednesday class doesn't meet Monday. So they have, let's see, that gives them all that time to forget everything. All right. Here's the maxim. Lights dissolve lights when it comes to forming solutions. Lights dissolve lights. Now, what does that mean? Well, if you're going to form a solution out of mixing a couple of things together, and it could be more than a couple, they have to have a like nature, or in other words, they have to be able to form common interparticle forces with each other, or they won't mix. Okay? So the real key to whether you can predict whether a solution is going to form or not is, can they form the same kind or similar kinds of interparticle forces with each other? And if they can, yes. If they can't, no. Just that simple. Now, we'll need plenty of examples, I think, for this. When it comes to what a solution is, it's a homogeneous, or some people will say homogeneous mixture of combining together a solvent and solute. Two components to a solution, solvent and solute. Solvent is the dissolving medium. Most of the time, what do you use to mix up solutions? Water. And if a solution uses water as the solvent, it's called very often an aqueous solution. So when you go to the cocktail party and there's a cluster of people chattering about aqueous solutions, they mean that water is serving as the solvent or the dissolving medium. Okay? And that's A-Q-U-E-O-U-S. I don't want to put the screen up just to write that on the board. All right. The other component is the solute. And that is the substance that is dissolved. All right? So, there we go. So, if we wanted to make an aqueous sodium chloride solution, what is serving as the solvent? Water. What would be the solute? Yes, the salt or the sodium chloride. All right? Now, you know that forms a solution, right? You know that. You've probably done it lots of times. Now, that's where we'll pick up Tuesday. We'll take a look at polar solvents and polar solutes and see what happens when we mix them together. enjoy the weekend, enjoy the holidays. This is the last one you'll get till Thanksgiving.
Like you can read that.
And when we have Thanksgiving break, we only have a week of class when we come back, and then it's final.
Like the color of the element, like the red one.
Probably week after next for the test.
On this one, it says liquid, a solid, but those look.
Yes, you'll get to use a periodic table.
Have a good weekend.
You too.